everybody. So it is my pleasure to introduce Brandon Wolding, who is joining us from NOAA series. He, I guess, first came to my attention when he was working on the Madden-Julian oscillation in graduate school, doing weak temperature gradient diagnostics of how initiation and how it evolves and how it's changing with climate change or expected to change with climate change. In his words, he's been moving downscale in terms of the types of convection that he's looking at since that time period. So he got interested in convectively coupled waves, and then more generic day-to-day convection, and even has a project related to shallow convection that he has worked on. I assume all this is because he's realized the importance of these smaller scales for the larger scale. I'm assuming that's been part of the motivation there. Yeah. He was a NOAA climate and global change postdoc. So those of you applying for postdocs are probably familiar with this. This is a highly competitive postdoctoral fellowship program. And he's now a research scientist. I should say he got his PhD from Colorado State University. And he, he is now a research scientist at NOAA. And he also has done some exotic travels. So I think when I first visited NOAA, he was off traveling from Vancouver Island all the way down to, the plan was to go all the way to Patagonia, and I guess they made it most of the way via truck. So quite a fun, extensive trip. And I guess I saw he also went to school in South Africa, so he's done all sorts of different travels. So yeah, so it's my pleasure to have him here today. I guess for those of you that know Vidget is off doing a postdoc with him as well. So we're pretty excited about that.
Yeah, absolutely.
Yeah.
Cool. I guess I should have asked this before I put the presentation together. Is this 45-minute talk with?
Yeah, 45, 50 minutes,
cool.
Something like that.
Questions as we go, or questions at the end, or how do you guys usually do? Okay, if you guys have questions, feel free to jump in here, because I tend to get rambling pretty quickly. But you can also save them to the end. So yeah, thank you. It's super great to be here. Thank you for the opportunity to speak. I'm going to be talking about ocean-atmosphere coupled energy budgets of convective discharge-recharge cycles. And for the sake of time today, I'm going to focus on kind of a smaller portion of this story, which is the special role that mesoscale convective systems, or MCSs, play in the energetics of these cycles. But as Larissa said, I've gotten really interested in the shallow convection and shallow convective organization recently. So if this is something that interests you, we can chat afterwards or during the Q&A portion. This is work done in collaboration with Juliana Diaz, George Coladas, and Maria Gaina from NOAA PSL, as well as Adam Rydbeck, Files and Med, Emily Riley Della Ripa, Jean-Chao Chen, and Isabel McCoy. And I don't give many citations throughout this presentation today, so I just want to acknowledge up front this is building directly off of some great work that's come from a bunch of people, but a lot of people coming out of this department as well. Kuni Inouye, Larissa, Vidget, obviously, and then some great work by David Raymond and Company, 2009. Adam Rydbeck had a great paper in 2022, which this is building off of, and Mapes and Neal, 2011, as well as a bunch of other stuff. All right, so the admittedly vague goal of this work is to better understand the relationship between clouds and their surrounding thermodynamic environment. Obviously, that relationship depends upon scale. So today we're going to be talking about spatial scales of roughly 2.5 degrees latitude longitude, so about 250 kilometers on the side. And we're going to be talking about day-to-day variability, or day-to-day variations. So what we're often talking about is the relationship between an ensemble, or population, or collection of clouds, and their surrounding large-scale average thermodynamic environment. So a little different perspective on this. This is satellite imagery from the Dynamo Field Campaign. This red inset here is roughly a 2.5 degree box. So big enough to contain a bunch of smaller convective elements. But if we looked at a different time, this whole box might be filled by a single mesoscale convective system. So we need some kind of narrative to describe what's going on in this photo to help us understand the processes at play here. And there's a bunch of different narratives that we can tell about this photo. I'm going to start with really a process level or kind of process-focused narrative. And forgive me, I'm going to read a little bit at length here, just to keep me on track. But as I'm reading, try to actually like visualize these processes going on, okay? So each day, solar insolation warms the upper tropical oceans, from which heat and moisture are transferred to the lower atmosphere via turbulent fluxes, acting to warm, moisten, and increase the moist static energy of planetary boundary layer air. Now our convective updrafts here, these guys, they carry this high moist static energy boundary layer air into the free troposphere, condensing water vapor to form precipitation and clouds. And those clouds shade the ocean from solar insolation, and they trap outgoing long-wave radiation in the atmosphere. The latent heat released within those convective towers helps to drive the atmospheric circulation, which in turn influences ocean currents and mixing. And these atmospheric and oceanic motions spatially redistribute the heat, moisture, and momentum over a wide range of scales. So we know that these processes, if we start thinking about long enough time scales, large enough spatial scales, that these processes can often be described by various forms of quasi-balance or quasi-equilibrium, right? And there are a whole bunch of narratives that we've developed around these states of quasi-balance, and I'm going to start by telling one of these, and we'll build from there. And this is a narrative of large-scale forcing and convective response. And the way this narrative goes is that our large-scale forcings, so think surface fluxes of heat and moisture, warming and moistening the near surface layer, maybe some large-scale convergence, radiative cooling aloft, these forcings are all acting to slowly drive the atmosphere towards instability. And the response of convection is to remove that convective instability. One way this might look in data is if we had some relevant measure of convective instability on our x-axis, and different people have different opinions about what measures of convective instability are most relevant, but just some relevant measure of convective instability. On the y-axis, we've got precipitation rate here on a linear scale. The black solid line shows the bin mean precipitation rate. So we can see when convective instability is really low, we've got no precipitation. As convective instability increases beyond what's often termed a critical point or critical threshold, we get this rapid pickup in precipitation with increasing convective instability. Now the black dashed line in the background here shows the PDF, the distribution of this measure of convective instability. And you'll notice it's got a really interesting shape. It's got this really long tail off to the left, and it's got a really kind of short, rapid drop off here to the right. And we could interpret the shape of this PDF through this lens of large-scale forcing and convective response, where this kind of large tail to the left is the result of our large-scale forcings slowly driving the atmosphere towards instability, and this rapid drop-off to the right of the critical point is the rapid removal of buoyancy by this convective response. And we can visualize these processes as really pushing towards each other and coming to some sort of semi or quasi or statistical balance here near the critical point, which is where we see the mode of the PDF, right? That's kind of the most frequently observed state of the system, or you can think of that as like a preferred state of the system, right? But we know that this narrative is too simple. We know that large-scale forcings themselves respond to convection. You can very easily see that in this photo, right? We see the shadows here at the base of these convective towers here impacting radiative fluxes. We know that wind variability near the base of these towers is going to change surface fluxes. And we know that latent heat released within these towers is going to very rapidly change the large-scale circulation of the tropics. So our large-scale forcings themselves are a response to convection, or they respond to convection. And maybe no problem has helped us realize this more than the problem of convective self-aggregation. So I'm going to show an animation here, courtesy of Nathan Arnold from his work with David Randall in 2015. They did this really kind of interesting and insightful model setup where they took a global version of SPCAM, super parameterized CAM. They ran it as an aquaplanet in a non-rotating framework, so we've stripped away all the rotational dynamics. And they force it by constant and homogeneous solar insolation, and constant and homogeneous SSD. So at the start of the simulation, our large-scale forcings are uniform. And we can imagine the simulation evolving in a couple different ways, one of which would be our uniform forcings would drive a uniform increase in convective instability. Convection would begin to respond and push back against that. And these processes could come to some sort of quasi-balance and kind of a uniform, homogeneous, light drizzly state across the planet. But of course, we know that's not what happens. You know, the simulation, the planet very quickly aggregates into these regions where we have enhanced total precipitable water in the blue color shading here, where we've got large-scale ascending motion. We've got this really moist column with really heavy convection, heavy precipitation. Surrounded by these regions of low total precipitable water, we've got large-scale subsidence. It's relatively dry, and we've got suppressed convection. So I show this to highlight two things. Basically, first of all, our large-scale source and sink terms, these things are evolving in tandem with convection. They are coupled to convection, and because of this coupling, you can get these very interesting feedbacks and very interesting behaviors. In this case, by the end of the simulation, if we look at our distribution of total precipitable water, it's not unimodal anymore. In this case, we've got a bimodal distribution with kind of two preferred states, one which is very moist and heavily precipitating, and one which is relatively dry and has suppressed convection. And in both cases, in these regions here, we've got a kind of a quasi or statistical balance of processes going on, right? But we know that, the real world is more complicated than a non-rotating aquaplanet. And it probably is fair to consider some variations in our large-scale source terms to be more forcing-like in nature. And I've got a few potential examples here on the right-hand side. None of these are black and white. They all fall on kind of some grayscale. But you can imagine the initial arrival of an oceanic Kelvin or Rossby wave into an area impacting surface fluxes is something that would feel more forcing-like from the perspective of convection, right? So to kind of circle back to the goals of the study, what we're really trying to do is understand this nuanced dance that's going on between convection and our large-scale source and sink terms, right? These things are constantly pushing and pulling on each other. Sometimes they're finding these states of balance. But this is all going on within the mosh pit of the tropics, right? So this dance is going to be interrupted a lot. We're going to have to sift through a whole bunch of other stuff going on here. So ambitious roadmap for the rest of the presentation here. I'm going to start by introducing an entraining Bloom model computation of vertically integrated buoyancy. This is going to be our relevant measure of convective instability for this study here. And once we've described this measure of convective instability, we're going to use it to identify and define convective discharge-recharge cycles. So if you've never heard of these, that's fine. I will introduce them here. Once we've identified these discharge-recharge cycles, we're going to look at some different observational data sets to try to characterize the cloud population and how it evolves throughout these cycles. And then we're going to turn to ocean-atmosphere energy budgets to try to understand the processes driving these cycles. And then we're going to finish up with an anecdotal case study from Dynamo to kind of try to integrate some of these ideas and show why they might be relevant. We're going to be looking at Indian and Western Pacific oceans only. We're using daily average 2.5 degree data, I-merge precipitation, AERO5 thermodynamics for the time period of 2001 to 2015. And when we get to the budgets, just know we've already removed the mean and the seasonal cycle. We're focusing on day-to-day variability. So we're going to be talking about variability about some slowly varying background, right? All right, so our relevant measure of convective instability. Lower tropospheric vertically integrated buoyancy. I'm just going to refer to this as buoyancy for shorthand. Basically, we're just calculating entraining cape, if you're familiar with that. This is an integrated measure of buoyancy, and we're going to be focusing on below the freezing level. So we're looking at just 1,000 to 600 hectopascals. And the way this calculation works is we initialize our plume, i.e. a parcel. This is just a fancy parcel calculation. Somewhere corresponding to roughly the subcloud layer in the tropics. So we're launching it at 1,000 hectopascals, and we're using our large-scale average, daily average temperature and moisture profiles. So we're ignoring all sorts of important kind of subgrid scale, higher frequency variability and organization, which we know is important. And then we allow this plume to rise, i.e. we lift our parcel. And as it rises, we're going to allow it to entrain or mix with surrounding environmental air, which again we're going to assume has these large-scale average thermodynamic properties. The entrainment profiles are user prescribed. We get to decide what they are. And in this case, we're using what's called a deep inflow B entrainment profile. And the hand-wavy description of that, for the sake of time, is really just the plume is mixing with its surrounding environment over a deep layer of the lower troposphere, all the way from the surface through the freezing level. This mixing is going on. And what the plume model outputs are estimates of the virtual temperature of the plume, which we can then compare to the virtual temperature of the environment. And the difference between the two gives us a measure of buoyancy, which we can then integrate in the vertical to get our vertically integrated buoyancy. So the way to think about this is really, this is just a coarse estimate of the ability of the large-scale environment to support convection. We also run this a second time where we turn entrainment off. So we're doing a non-entraining plume calculation. Because by comparing our deep inflow B buoyancy to our non-entraining buoyancy, and looking at the difference between the two, we can measure the buoyancy modification due to entrainment, due to those mixing processes. So I've got an example on the right-hand side here. This is from the first day of the Dynamo Field campaign. Nothing special about this profile. We're looking at the northern sounding array, so this is roughly like a 10 degree by 10 degree box. This is field campaign data. The solid line here shows the virtual temperature profile averaged over that 10 degree box. And when we run the plume model, where we've turned off entrainment, if we looked at the dashed line here, we can see it lies to the right of the environment, which means the plume is warmer than its surroundings. It's positively buoyant. That corresponds to the red color shading. If you integrated that in the vertical, that would give you your buoyancy measure. Now the dotted line here on the left-hand side is the virtual temperature of our plume with deep inflow B entrainment. You can see it lies to the left of the environment, i.e. it is negatively buoyant. This is convective inhibition, essentially. And so the blue color shading here would be our deep inflow B buoyancy. And the impacts of entrainment are just the difference between the dashed and the dotted line here. So the integrated area, the total color shading there, essentially. So we've got our measure of convective instability. Let's now use it to identify and define our convective discharge-recharge cycles. And I want to start by highlighting that everything that we're going to see today is buried within this very simple relationship, which we used to tell this forcing and response narrative. Okay? So in this case, we've got our deep inflow B buoyancy on the x-axis. We've got precipitation rate on the y-axis on a linear scale. And I'm going to change this figure in two ways. I'm going to change this scale to be a log scale. So we're going to be considering precipitation over kind of a larger range of precipitation rates. And I'm going to, instead of looking at the PDF of just buoyancy here, we're going to look at the joint PDF of both buoyancy and precipitation rate. So that's what we're looking at in this figure. Again, buoyancy x-axis, precipitation rate y-axis on a log scale. Color shading is the joint distribution, the joint PDF of these two. So you'll note it has a single mode here and generally slopes from the lower left to the upper right-hand corner of this figure, which tells you that generally precipitation rate increases with increasing buoyancy. But for any fixed value of buoyancy, we've got a very large range of possible precipitation rates, 2 to 3 orders of magnitude, which says there is a lot of variability around that generic relationship, right? So we're interested in variability, and specifically we're interested in how these two fields, precipitation and buoyancy, i.e. convection and convective instability, how these two fields co-evolve in time. So to answer this question, we're going to separate our data into bins along the x and y axes. And then within each bin, we're going to look at the bin mean temporal tendency of both precipitation rate and buoyancy. We're going to plot that as a vector, the vector tail at the bin center. So the vectors here represent the temporal co-evolution of these two fields, right? How these two fields co-evolve in time. We've got a log scale, so the y aspect of our vectors is really exaggerated down here and really compressed up there. But we can generally see that we've got two regions of cyclical behavior. We've got this region of clockwise cyclical behavior here, which is limited to lower precipitation rates. So we're going to generically refer to this as the shallow convective discharge-recharge cycle. And then we've got this region of counterclockwise coevolution here, which achieves higher precipitation rates. So we're going to refer to this as the deep convective discharge-recharge cycle. And kind of a generic definition of a discharge-recharge cycle would just be the cyclical amplification and decay of convection, coupled to cyclical increases and decreases in some relevant measure of convective instability. And you can see these discharge-recharge cycles using different variables, not just buoyancy, but column saturation fraction, moist static energy. There's a bunch of different ways to look at these. Their estimated timescales are between 10 to 40 days, though that's not very well constrained. And again, we've got these two overlapping cycles, which become more evident if you look at, for example, the probability of moistening or drying within each one of these bins. So in this case, regions of warm color shading show the probability of increasing column saturation fraction. So warm color shading corresponds to moistening. The cool color shading corresponds to a proclivity to dry. But if you look at these probabilities, they only span from 40% to 60%. So we're not talking about a highly deterministic evolution here, right? There's a whole bunch of other variability going on. So to say that in a different way, the evolution in reality often differs from the vectors you see here. They really only emerge when you consider kind of many realizations of this here. There's a lot of other, dancing going on. All right, so we've identified these cycles. Now let's try to characterize the cloud population. We've looked at probably 6 or 7 different observational data sets to do this, to characterize cloud depth, precipitation type, organization of deep convection, organization of shallow convection. Today we're just going to look at 2 products. We're going to start by looking at the mesoscale organization of deep convection, and then we're going to look at a CloudSat product, which gives us a more nuanced, kind of more exciting view of the clouds, in my opinion. So we're going to start by looking at mesoscale organization. We know that deep convective clouds in close proximity can aggregate upscale into mesoscale convective systems. And these are important because they induce circulations on scales larger than and persist longer than the individual up and down drafts which make them up, right? So they're an entity which helps transition scale. They help transition us from the convective scale to the synoptic scale. They're often referred to as building blocks of larger scale convective variability. And we're really interested in these because they have humongous energetic impacts. This busy schematic from Bob Howe's paper here, I've highlighted a few of kind of the important features of MCSs. They've got both convective scale and mesoscale downdrafts, which transport low moist static energy air downwards. So MCSs tend to have this organized inflow near the freezing level, which corresponds roughly to the climatological minimum in moist static energy. So they're bringing in low energy air, they're transporting it downwards, and they're pushing out high energy air, right? So it's a net export of moist static energy. We know that the cold pools of MCSs enhance surface fluxes, ocean to atmosphere surface fluxes greatly. And we know that these big stratiform anvils greatly impact both shortwave and long-wave radiative heat. So we expect these things to have big energetic impacts. And so the database we're using to look at this is from Zhe Feng and Company 2021. It's an MCS tracking database that basically takes iMerge precipitation and classifies it as either MCS, deep, non-MCS, or non-deep, where MCS precipitation, hand-wavy description again, is just sufficiently deep large and long-lived enough. Our deep non-MCS precipitation is sufficiently deep, but it either doesn't meet the large or long-lived enough criteria, and then non-deep is non-deep, right? So in this figure here, we're looking at the fraction of the total precipitation rate. The color shading shows the fraction of the total precipitation rate, which is given on the y-axis, that comes from our non-deep, non-MCS deep, and MCS components. So if you add up the color shading in these three figures, they add up to 100% of your precipitation rate on the y-axis. So the way that you would read this figure would be down here when our precipitation rates are low, it's predominantly non-deep precipitation. Makes sense. As precipitation rates increase, we see more non-MCS deep precipitation. And then at precipitation rates greater than roughly 10 millimeters per day, that's coming predominantly from mesoscale convective systems. So this tells us two things. It tells us, first of all, this deep convective discharge-recharge cycle is associated with changes in mesoscale organization. This is important from like a parameterization standpoint. Like, do we need to parameterize this when? And it tells us that later on, when we're looking at our energy budgets, we should expect to see some pretty big changes in radiation, surface fluxes, and moist static energy transport. So the second data set we looked at was a CloudSat cloud type analysis. This was a data set produced by Emily Riley and company back in 2011. And basically, they identified echo objects as contiguous regions of cloudiness. And then each echo object was assigned a cloud type based on the echo object base height. So where did cloudiness start? Echo object top height, where did cloudiness end? And echo object width, okay? So I'm gonna walk you through the different cloud types. We're gonna start with shallow clouds, go to mid-level clouds, and then go to deep or upper-level clouds. And I'm gonna show little snippets of these clouds in the lower portion here. This x-axis corresponds to roughly 500 kilometers or so for scale. So we're going to start with shallow cumulus. So shallow cumulus is defined as starting near the surface, but being limited to below the freezing level. So tops are limited to below 4.5 kilometers. And these things are relatively narrow. They're less than 10 kilometers wide. Then we've got the relatively wide stratocumulus. These have the same criteria, but they're greater than 10 kilometers wide. If we go up to our mid-level clouds, we've got congestus. These start near the surface. They extend to between 4.5 and 10 kilometers, so between the freezing level and where water freezes homogeneously. And then we've got our alto-strato and alto-cumulus clouds. So these start a little bit higher. They start above 3 kilometers, and they go to between 4.5 and 10. And then we've got our deeper upper level clouds. So we've got narrow deep precipitation, start near the surface, go above 10 kilometers, but relatively narrow, less than 200 kilometers wide. Wide deep precipitation is greater than 200 kilometers wide. We've got still relatively thick detached anvil. The base starts above 3 kilometers, the top extends above 10 kilometers. And then our relatively thin cirrus clouds. So the base starts above 7 kilometers and the tops extend above 10 kilometers. So we've got all these cloud types, and in the next figure I'm going to show you where each of these cloud types is preferentially enhanced throughout those cycles. So very busy figure. Color shading is basically the green color shading shows you where that cloud type tends to be enhanced. We've got our shallow clouds, cumulus and stratocumulus down here. Our mid-level clouds, congestus, alto-strato, alto-cumulus here. And then our deep or upper level clouds, narrow deep precipitation, wide deep precipitation, detached anvil, and cirrus. So I'm going to walk you through each one of these discharge-recharge cycles, and we're going to characterize the evolution here. So let's start with the deep one. So if we start in the lower right-hand corner of each one of these panels, and we trace that counterclockwise circle, right? We're going from shallow cumulus to congestus, to narrow deep precipitation, to wide deep precipitation, to some mix of detached anvil, alto-strato, alto-cumulus, and then back to cumulus. So this is a very familiar progression of clouds if you study deep convection in the tropics, right? You see this in equatorial waves, you see it with the MJO. So this is something that was like very familiar to us. The shallow convective discharge-recharge cycle is a little more interesting. So we're going to start in the lower left-hand corner. We're going to try to trace a clockwise circle, and we're going from basically enhancements of cumulus to enhancements of the relatively wide stratocumulus, and then kind of through some mixed cloud population, but back to cumulus. But interestingly, this is all happening in the presence of widespread upper-level cirrus clouds. So our two predominant enhanced cloud types are limited to well below the freezing level, but we've got a whole bunch of upper-level cloud going on there. And this is an image of one of the days, which was identified as being a shallow cumulus day here, to give you an idea of what this might look like. All right, so now we know how the cloud population evolves. We want to turn to our ocean atmosphere energy budgets to try to characterize the processes driving this evolution, these discharge-recharge cycles. And our starting point is going to be the atmospheric moist static energy budget, right? We know in the tropics, the moist static energy tendency approximates the column moisture tendency, right? So we're describing the evolution of how moist the column is. And we're relating it to transport processes, horizontal and vertical advection, surface fluxes of heat and moisture, and radiation, okay? And I've got each one of these terms plotted here. Don't bother trying to interpret them right now, right? The first thing I want to note is that when we look at these processes, they're all plotted on the same color scale. Surface fluxes are clearly a first order term here, right? So what that tells us is that the ocean is acting as an important energy source or sink, and so we should consider the upper ocean in this analysis. So we're going to take a little detour here for a second, and we're going to look at the tendency of the sea surface temperature and then ocean heat content averaged over different layers of the upper ocean. So 0 to 10 meters, 0 to 50 meters, 50 to 100 meters, and 350 to 400 meters here. So we see in the upper right-hand corner where we have most of our mesoscale convective systems, SST tendency is negative. The sea surface temperature is cooling, up to 0.1 Kelvin per day, which is actually pretty considerable when you're talking a 250 kilometer area. And then when we've got light precipitation, but in a relatively unstable environment, the SST tends to be warming. And this cooling and warming of the SST is mirrored by changes in upper ocean heat content, which are limited predominantly to the upper 50 meters of the ocean. Right? So what we're interested in is predominantly happening in this layer. And just like we've got an atmospheric moist static energy budget, we've got a budget to describe the evolution of ocean heat content over that layer. And just like in the atmospheric moist static energy budget, our ocean heat content tendency is just the result of transport processes, so oceanic motions redistributing this energy, surface fluxes of heat and moisture, and radiation. And if you compare these two budgets, they share surface flux terms, and they share radiative terms at the ocean-atmosphere interface. So something cool happens if we add these two budgets together. The resulting budget is actually simpler than either of these two budgets, right? Our air-sea interaction terms, our surface flux terms cancel out, and our radiation term here simplifies to just net radiation at the top of our column, which is 100 hectopascals, and penetrative shortwave at the bottom of the column, which is negligible at 50 meters, if you just ignore that. So this tells us that our change in kind of combined ocean-atmosphere coupled energy, the combination of moist static energy and ocean heat content, that tendency is driven by just transport processes, so atmospheric and oceanic motions moving energy around, and then net radiation at the top of our column. So now we've got our budget framework in place, we can ask some questions. We can go back to our mesoscale convective systems. We can ask, how do MCSs impact ocean and atmosphere energy budgets? And remember, our MCSs are in this upper right-hand corner of each panel here, right? So let's start with the moist static energy budget. What is it telling us? Well, we can see that mesoscale convective systems are rapidly exporting moist static energy. We talked about that through the circulation. And this export of moist static energy is being supported by two feedbacks. A radiative feedback, this is a reduction of long wave cooling to space, and a surface flux feedback, this is enhanced fluxes from the ocean to the atmosphere. And these two feedbacks are strong enough that when we look at the total moist static energy tendency, it's pretty close to zero, right? This looks like a rather balanced situation, which means that it looks sustainable. Like this could go on for a long time if you consider it just from the perspective of the atmosphere. But when we turn to the upper ocean heat content budget, we can see that the upper ocean heat content is dropping very rapidly. And this is predominantly a result of reduced shortwave heating of the upper ocean. And again, this ocean to atmosphere transfer of surface fluxes, right? So when we consider the combined ocean atmosphere energy budget, we can see this, this is not a sustainable situation. Your column is just bleeding energy at this point here, right? So this is where the ocean gives us a different perspective than if we consider just the atmosphere alone. Something else, MCSs appear to be pretty unique in their ability to rapidly discharge ocean heat content. None of these other cloud populations are rapidly discharging upper ocean heat content. So that tells us something about the relative uniqueness of mesoscale convective systems and why we care about them. Now, stepping back just a little bit, just considering this figure more broadly, because it has some pretty cool takeaways as well. Notice that the variability in the processes impacting moist static energy, so these three terms, they're of the same order as the processes impacting ocean heat content, right? They're comparable in magnitude. But the processes impacting moist static energy are considerably more balanced than the processes impacting ocean heat content, right? So what this means is that these processes, and particularly transport processes, they can drive changes in atmosphere-ocean coupled energy. But that's going to be mainly realized as changes in ocean heat content. You're not going to see it as changes in moist static energy. The other thing that's kind of interesting is when you look at our radiative feedbacks, they almost completely cancel under all these different cloud regimes here. So that's interesting because it tells us that radiative feedbacks are actually pretty similar to surface flux feedbacks in that they're redistributing energy between the atmosphere and the ocean, but they're not causing a change in the total quantity of moist static energy and ocean heat content here. All right, so to finish up a case study here from the dynamics of the Mag-Julian oscillation or dynamo field campaign. This happened in 2011. It went from October 1st to December 31st. We're going to be focusing on data from the northern sounding array here. We're using CSU quality controlled kind of array averaged variables. And just a reminder, because we're going to be looking at averages over this domain, when you take averages, you're ignoring all sorts of really interesting and important variability. So just a random snapshot from a day of shallow convection, like all sorts of beautiful and important organization going on here, a day of relatively deeper convection, right? All of this stuff gets washed out when you take averages. All right, so the more boring average perspective on this stuff. So we've got the dynamo time period, October, November, December. This is array average precipitation, where we've added a 10-day running mean to pull out the kind of slower variability here. You see you've got 3 periods of enhanced precipitation corresponding to 3 MJO events, and they're each preceded by periods of relatively suppressed precipitation here. If we just look at the daily mean time series, so we don't do our 10-day running mean, we can see a lot more day-to-day variability within these 3 periods. All right, so as a starting point, we're just going to plot these 3 periods on those same diagrams that we were looking at earlier. All right, so we've got our 3 periods plotted on our 3 diagrams. The start of each period starts with the kind of more clear or white colors and moves towards the saturated colors. So I'll kind of walk you through these. So our October event started here. We're worked its way down, bounced around, spent a lot of time up here near this kind of deep convective attractor, and worked its way down here. Our second event worked its way up here, did a couple spins, works its way down here. And then our third event, again, just like the first two, works its way up here, spins around a little bit, and then does this really big transition at the end of period 3, where all of a sudden our measure of convective instability drops very rapidly, and we get pushed to the far left-hand side of this diagram. So something interesting happened here. If we attach some imagery to this, we can see that on the day of kind of peak precipitation, where we've got high instability, we had big mesoscale convective system activity. About a week later, this transition took about a week. We've got this case where, as we kind of expected to see, shallow cumulus with overlying cirrus, we see that is indeed the case, so it gives us a hint as to where all of those cirrus clouds were coming from. Then a few days later, we'd expect to see more shallow, but kind of more stratiform-y, wider cloud figures. Maybe that's going on, hard to say. So I saw this, and I was like, oh, I wish the Dynamo Field campaign would not have ended right here, because I was really curious what happened. So I went back and I stitched in I-merge precipitation averaged over the northern sounding array, and I used Era 5 thermodynamics instead of the field campaign thermodynamics. Did some comparisons. They compare pretty well, at least good enough for the qualitative bit that I'm going to show you here. But in period 4, we see that after that large kind of discharge of convective instability here, we ended up staying here in these relatively suppressed precipitating conditions, for probably 5 to 6 weeks afterwards here. So this is an extended period where we had suppressed convective conditions. So I wanted to look at how this related to moist static energy and ocean heat content. Again, these black time series is the same precipitation time series that we looked at before. We've got our 3 precipitation events here. And moist static energy anomalies are plotted in the red here. So we can see that our 3 periods of enhanced precipitation are basically bracketed by this period of enhanced moist static energy, as we would expect, right? And our suppressed convection corresponds to periods where our moist static energy was, neutral or anomalously low. And then if we look at upper ocean heat content, this is kind of interesting. Upper ocean heat content starts quite high. And with the first event, we get this kind of drop of ocean heat content with increased precipitation. After the period of increased precipitation, we get a rebound in ocean heat content. And then at the start of this next event, we start to get a decrease in ocean heat content. And then we get a really rapid drop in ocean heat content with this big spike in precipitation, presumably MCS activity. And then we've got a short period in between where we got suppressed convection. So we get this kind of impartial recovery followed by another deep convective event, another drop in ocean heat content. And so by the end of this period, we've gone from having anomalously high ocean heat content to anomalously low or close to neutral ocean heat content. So a few things about this that correspond to our previous analysis. First of all, the overall ocean heat content variability is a lot bigger than the variability in moist static energy, right? So again, going back to that balanced versus unbalanced perspective. We see that the repetitive discharge here changed our ocean heat content surplus to an ocean heat content deficit. And so this kind of poses the question whether ocean heat content limits the ability to support consecutive or sustained periods of deep convection. Think like primary versus successive versus terminating MJO events, right? So in summary, we work to identify shallow and deep convective discharge-recharge cycles. We use different observational data sets to characterize how the structure and organization of clouds change throughout those cycles. And then we tried to relate that to specific processes using combined ocean and atmosphere energy budgets. And as far as relevance goes, like why NOAA is concerned about this, is we're making a big push in coupled model development right now, ocean atmosphere coupled weather and climate models. So we need some sort of guidance, like are clouds doing our models doing the right thing in terms of coupling clouds to these flows of energy into, out of, and between the ocean and atmosphere. So we're hoping to use this as a model diagnostic to see how the models are doing and provide some specific guidance as to what cloud types they're struggling with the most. Hopefully this will give us a better understanding of how organization impacts how energy flows through the Earth system, you know, go beyond just thinking about shallow and deep, but spatial organization of convection. And then predictability. This is something that I don't think we're going to have time to look at anytime soon, but I think would be a really promising research avenue, is like incorporating ocean heat content into understanding primary versus successive versus terminating MJO events. And this, you know, whether that can tell us anything about how, you know, the proclivity of the atmosphere to get stuck in either a shallow convective regime or a deep convective regime and the transitions between it. So, yeah, that I guess I'll just say thank you for having me here. It's been a wonderful visit. I'm happy to answer any questions you guys have.
So we usually have students ask the first questions. Are there any student questions? Yeah.
Yeah, thanks so much for the talk. That was very well articulated. My question is, is the ocean heat content budget closed? In the sense that does the MCS rain cold water on top of the ocean?
Yeah. We calculated this in a very specific way for a very specific reason. Let me go back to the actual equation so I can point this out, right? So like, what terms in this do you trust and what terms of this do you not trust? Well, hopefully, especially with like Argo floats and stuff, we can constrain the tendency of ocean heat content well enough. We can measure the state of it with enough consistency to tell us how it evolves, right? Surface fluxes of heat and moisture, we trust them to the same extent that we trust Air 5, surface fluxes of heat and moisture. Not perfect, but hopefully to the first order correct. And same thing with radiation terms. The big terms in question here are obviously the transport terms, and these things are not very well constrained at all. So in practice, this budget, the residual was lumped into, you know, so you could calculate each one of these terms explicitly, or you could calculate one of them as the budget residual. In this case, we calculated the kind of the vertical convection as well as the kind of diffusion mixing terms as the budget residual. But I want to step further and say, like, I'm just not even going to break apart these individual transport terms, and I'm going to call them all transport. And so the idea is to basically choose the one that you're most uncertain with, calculate that as the residual, and not try to pick it apart or pull it apart too far. Interesting side note on this is Adam Rydbeck and I have been looking at these type of budgets with ENSO and looking across different ocean reanalysis products. And if you look across ocean reanalysis products, they span the whole spectrum of what terms are doing the transport here. There's no agreement on them. Like the ocean heat content, you know, these terms are relatively in agreement, but the transport terms are all over the board. So I don't have much faith in hanging my hat on any one of those terms there. That's a great question. Yeah, thank you.
Thank you.
As a follow-up to that, I think it would be really interesting to see where it's going, because the two things I can imagine the MCS doing are either if it's mixing deep enough to like get below the mixed layer and you're really mixing heat down deeper into the ocean, or if it's some sort of wind-driven process where you're transferring heat outward, and then I imagine that could lead to not only are you making one region less convectively plausible, but you're also seeding new regions for new convection. So this is really interesting. It would be it would be really interesting to see where the advection of that heat is going as well.
Yeah, totally agreed. I started, like, as a little side project a couple months ago, I started to look at some of the buoy data that was kind of in the Indian Ocean region there, and had an MCS tracking database and just like matched them up and looked at MCS passages and then looked at how that signal in ocean heat content. So it's not isolated to just the, you know, advective terms. You've also got radiation in there, but to look at how that kind of moved downwards with time after the passage. And I didn't get very far in that analysis, so I have no idea. But yeah, would be super interesting to look at, and I think super important too, for sure. Yeah. Sean?
I'm going to build off that. You know, one of the interesting things about the December active period versus October and November is October and November were widespread, stratiform, long-lasting, random kind of embedded convective within. December were a quick succession of rapidly moving small lines associated with a strong westerly wind burst. And so this was my question related exactly to that.
Yeah.
How much do you think it would, like, did that matter? Did the mode matter? Does this scale with the overall MCS size or how it's organized? Is it the fact that October, November had such wide coverage for such a period of time, or is accounting for that really strong westerly wind burst over a long piece of time in December important? Like, how would you sort that out? It's really interesting.
Yeah, no, that's a super fascinating question, and like I didn't participate in that field campaign, so I don't have that kind of personal insight. So that's like super interesting to hear those like on the ground differences between those events. In terms of like how you actually sort through that, you know, I think if you had a budget that you believed close enough in terms of, you know, your tendency, your surface fluxes, and your radiation, you're calculating transport as the residual, like looking at those events one at a time and seeing if transport all of a sudden plays a really big role in, like, say, the last event where you've got like organized, like kind of longer westerly wind bursts that could spin up like coherent oceanic circulations. Certainly would be, you know, maybe those stand out in those type, like the transport terms stand out in those events versus the shortwave radiation. I mean, if you got deep convective clouds, that term is going to be there event to event, you know, so there could be something unique about kind of wind structure in those events. And Adam's also done some really interesting work looking at kind of MJO wind bursts inducing oceanic Kelvin waves, which then reflect off of the maritime continent and propagate westward as oceanic Rossby waves. And their arrival in the western Indian Ocean, not consistently, but sometimes times up with they'd be downwelling Rossby waves, so they'd lead to kind of a warming of the near surface layer, and that has timed up with the onset of subsequent MJO events. So there's also that kind of stuff which can factor in these transport terms of like I was saying, those like more maybe forcing like terms of like just something rolling into the area and driving one of these terms away from the generic relationships that we're seeing here. You know, again, these evolutions are all like 60-40, so it's kind of, you know, other things have a big role in determining what's going on in processes. Okay.
Is there any sort of discharge or cycle observed over land, or do you find the ocean interactions are necessary for that to occur?
Yeah, good question. I haven't spent a lot of time looking over land, just because land tends to be a little bit more challenging, to be frank, and especially when you're looking at like these entraining cape measures, because obviously the characteristics of your surface parcel play such a role in this, and you've got these huge swings in that over land, which may not be super well constrained. I'm not exactly sure. Looking at it through kind of more generic measures like column saturation fraction, you'll see these cycles, but they tend to be quite a bit more muted, it seems like. But it's certainly a great question in that, like, from an energetics perspective of like, you know, we get MCSs over land, right? Oftentimes you'll hear people talk about, you know, MCSs over like North Africa, you know, an MCS will roll through, it'll, you know, maybe dump a bunch of rainfall over an area, and then you won't have MCSs for a couple days afterwards because the surface isn't able to warm up enough. But just this, the difference between the ocean being able to act as this big energy reservoir, which takes a long time to discharge, but also a long time to recharge, versus land, I think is, maybe be a really kind of fruitful way to view it with this kind of energy budget. And yeah, role of soil moisture, which will be interesting as well. Yeah. HC.
My question might be overlap with previous questions, but I want to ask, sometimes we see the balance between the vertical convection of MSE and the long-wave radiation flux. So I'm curious about if we see that self-balance in the other questions, in the other two budget equations, like the ocean content budget and the other budget.
Right. Yeah. So in the ocean budget, I wouldn't again trust this enough to pull out like any single one of these terms, but you can kind of look through these diagrams and compare for states of balance between these two, right? This sticks out like a sore thumb here in the moistatic energy budget, and you've basically got something similar, not quite as balanced here going on there. But in the ocean heat content budget, you don't see these dominant balances between the transport terms and the radiation terms necessarily. And the difference in dynamics is in the atmosphere, you've got tropical weak temperature gradient balance, like obviously linking together the circulation and the heating terms very tightly, which that's kind of missing in the ocean. So I guess maybe we would expect that to some extent. Yeah.
Other questions? Okay, well, let's thank our speaker. Yeah, if you have any additional questions, feel free to.
Yep, I'm happy to hang around for a while. So.